So in section 4.3, we're going to discuss increasing and decreasing functions using what's called the first derivative test. The first derivative test really is the result of an observation that you can make using the mean value theorem. So let's remind ourselves real quickly what the mean value theorem is all about, what it says. The mean value theorem says that the slope of the secant line of a function, basically the line that connects these 2 points, that slope is equal to the slope of the tangent line, or the derivative of the function at some point. So we'll see that summarized like this: f prime of x equals f of b minus f of a over b minus a, like that. So here's your function. Here's f of a. Here's f of b. And at some point, the slope of the secant line, basically this line connecting the two functions, equals the derivative, or the slope of the tangent line. So where would that be? In this case, maybe right here would be a good point for that. Let's take a look at that quotient here. F of b minus f of a over b minus a. Now, in the case of an increasing function like we have here, then, well, b minus a, since b is to the right of a, b minus a always has to be positive. What about f of b minus f of a? What's the sign of that going to be when I subtract these two? It's also going to be positive. Now keep in mind this is equal to f prime of x. So what that's saying is that for an increasing function, on an interval where it's increasing, the derivative has to be greater than 0. F prime of x has to be greater than or equal to 0 for an increasing function. What about a decreasing function? Well, if we repeat this for a decreasing function, then again you have f prime of x equals f of b minus f of a over b minus a. This time we're looking at it for a decreasing function. B minus a is still positive. But for a decreasing function, here's f of a, here's f of b. What's f of b minus f of a going to look like? It's going to be negative. And overall, a negative divided by a positive is negative. So when a function is decreasing on an interval, its derivative is going to be negative. When it's increasing on an interval, its derivative is going to be positive. So where the derivative is positive and negative tells us a lot about the function. Helps us get an idea of the shape of the function. Let's practice this with a bunch of examples. Along the way, one of the things I want you to pick up is a little factoring trick that we practiced for the last test, but could use some more practice now. So f of x is increasing and decreasing. We want to figure out what intervals it's increasing and decreasing on. F of x itself, in problem 6, is a pretty congenial function. It's a nice polynomial. X to the fourth minus 2x squared One thing that's nice about it is that it's a polynomial function, meaning it's defined everywhere, right? Its domain is negative infinity to infinity. Let's take a look at f prime, because f prime is going to tell me things about where it's increasing and decreasing. That's going to be 4x cubed minus 4x. Okay. Now I want to know where it's positive and where it's negative. And part of what helps me decide where it's positive and negative is knowing where it can change signs. In other words, knowing where it's actually equal to 0. So 0 equals 4x cubed minus 4x. Well, how do you solve this? factor would be a good way. So I'd take out the 4x, that leaves behind x squared minus 1. And that further factors is 4x times x minus 1 times x plus 1. Can anyone read off the solutions here? Good. 0, 1, and negative 1. Now, if you'd like to borrow a ruler, I have a few left that haven't wandered out of the classroom with people, so come on up. But we're going to draw ourselves a little bit of a chart here. So we're going to keep track of some information. X, F, F prime. And on this chart, let's put the points that we found down here in order from lowest to highest. So negative 1, 0, and 1. Moving across from left to right. Here. Okay, so we need to decide, is the derivative positive or negative in between all these points? To help decide, is the function increasing or decreasing? Now what I suggest is that we let our calculator do a lot of the work for us. So I'm not going to worry about the function. I'm going to program in the derivative. So take out your calculator. Hit the y equals key and let's program in the derivative. So clear out anything that's there. 4x cubed minus 4x. Now there's a setting that we adjusted a while ago, and that was for your tables. Let's make sure that it's set up the proper way. Hit the second key, then the window key. Make sure your independent is set to ask and the dependent is set to auto. If not, then cursor over, put your cursor on ask and press enter. With that setting correct, then hit the second key, then the graph key. This will take you to the table menu. And what this will allow you to do is type in all the values of x that you want. Hit the delete key up here next to the mode key and get rid of any values that might be there. And now let's look back at our little chart here. I need to test some points in between all these values. So what would be some good test points? Something to the left of negative 1. Negative 2. What would I use here? Negative 1/2, 1/2, and 2. Okay. So let's see what our function, at least the derivative, looks like in these intervals by typing in these points that I have here in yellow. So negative 2, negative 0.5, 0.5, and 2. Now I don't really care about the exact values I get for the y coordinate here. Does anyone know or can tell me what information am I looking to see from this menu? Positive or negative? I just want to know, is the function increasing or decreasing? And what tells me that is just the sign of this in that interval. So those signs alternate. They start out negative, positive, negative, positive. So in this case, they alternate. They don't always have to. If they do, great. If they don't, that's fine too. But what's that telling me? If the derivative is negative, what's that saying about the function? It's decreasing, right? So the function's decreasing here, then increasing, then decreasing, then increasing. Yay. So, wow, that's great. In fact, notice we haven't graphed the actual function itself, But because of the shape of this, that's telling you what's going on at -1. If a function is decreasing and then starts increasing, what had to happen at that point, say -1? Yeah, there's a horizontal tangent, meaning that -1 is a minimum point, right? The function was decreasing, then it changes directions, has a horizontal tangent, then starts increasing. So it had to, at some point, pass a minimum. And that's what this is. -1 is a minimum. All right. What's that saying about 0 then? Yeah. Now I should probably put R here, meaning R being relative minimum, relative max, because there could be bigger numbers or smaller numbers, but in the neighborhood near 1, or the neighborhood 0, -1, these are relative mins or relative maxes. Okay, that's a nice bonus that you get because we have such a cool chart here. What the problem was getting at, though, was asking you, where is it increasing? When you talk about increasing and decreasing, it's always intervals along the x-axis. So along the x-axis, well, it's decreasing from -infinity to -1. So -infinity to -1. Then it starts increasing. It starts increasing from -1 to 0. And then it's decreasing again. So union 0 to 1. And finally, it finishes up by increasing from 1 to infinity. So as far as the problem is concerned, as far as the book is concerned, this is the answer that they're looking for. This was just kind of a little bit of a bonus, but I like this style of table because it helps you understand a lot about the function. Okay, so watch out because I'm about as good as Andre Drummond. All right, told you. All right. Yeah, U's for union. It means or, so it's this or that, or this in addition to that. So it's decreasing on both of these intervals. So you're adding those two intervals together is what it's saying. Intersection, because intersection looks where they overlap, and there's no overlap here. Yeah, so good question. Anything else on the first one here, number 6? Let's move up to problem number 12. Problem number 12 is going to be a little bit of a replay, but there's also going to be a little bit new as well. Y equals x plus 9 over x. Now, on the exam that you just got back, one of the things I suggested is that, in doing derivatives, you might want to think about rewriting these things or reworking them somehow before you differentiate. And this is a good example. Instead of using the quotient rule here, it's much more convenient to write that as 9 plus, or x plus 9x to the negative first. It's just going to be easier to differentiate this. This isn't bad here, though, because here it's a little bit easier to see the domain. What can you tell me about the domain of this function? Everything but 0. So everything but 0. X not equal to 0. But here's the thing. The function and its derivative can actually change signs there. So we need to figure out where this function can change signs. Let's worry about the derivative first. So dy by dx. And for that, I'm going to look at the second form of this function. Cleef, what will be the derivative here, please? Perfect. I'm just going to write that as 1 minus 9x to the negative second. Good. Let's set this equal to 0 and solve. So set that equal to 0. I'll move that to the other side. 1 equals 9. X to the negative 2. Or how about 9 over x squared? Multiply both sides by x squared. I get x squared equals 9. So what does x equal? Plus or minus 3. So the derivative could change signs at 3, and at negative 3, and at 0. So dy by dx can change signs at x equal negative 3, 0, and 3. So we have to test the derivative at those 3 points, or actually in between all those 3 points. Because, and maybe I should write it this way, 1 minus 9 over x squared, the derivative is undefined at 0. So the derivative could change signs from the left of 0 to the right of 0. We just have to test it. So now, 0 is not a critical point because 0 is not in the domain. But nonetheless, the function could have a change there. So let's write ourselves a little table. So x, y, and y prime. I said little table. I'm going to give myself actually a generous amount of room here. Let's test those 3 points. So negative 3, 0, and 3. Now, a little bit of mathematics notation here for us. At negative 3 and 3, the derivative is 0. But what about at 0 itself? What can you tell me about the derivative there? Undefined. So you can write undefined, UND, or there's a mathematical symbol that I like. This stands for there exist. And if you put a little slash through it like that, then it means it doesn't exist. It's just my fancy way of saying, all right, it's undefined here. That's fine. What we need to do is we need to test some points in between here. And this is where it's much nicer to do it on a calculator than it is to do it by hand. You can do it by hand. There's nothing wrong with taking some points. Like what would I test here to the left of negative 3? Negative 4. Negative 2, 1, and 4. Test whatever points you want here. I mean, in this last interval, you could test pi, or pi squared, or pi to the 5th power, whatever you want. But, you might as well make it easy on yourself. What function should I be putting into my calculator? The derivative, all right? So you want to put in this function, or you can type it in like that. Doesn't matter either way. But we want to test the derivative. So let's hit the y equals key and type in 1 minus 9 divided by x squared. And then go to the table function. So hit the second button, then the table. Do yourself a favor, just so you don't get confused. Start by deleting all those points that are already there. That way you don't look at them and get messed up. Negative 4. What else do we say? Negative 1. I said negative 2, so we'll stick with negative 2. 1, and then 4. Nice. Dylan, what's the relevant information that I need from this chart? Perfect. Whether they're positive or negative. Now, if these numbers get a little bit too small, you can't see them, then put the cursor on the y values, and then you see a nice zoom in of those values down here. So the relevant information then for us is positive, negative, negative, positive. That's what we needed. So let's fill that in here. So positive, negative, negative, positive. See if you can't tell me what that's saying about the function. That's true. It's a nice observation. Well, what's happening to the function here? Yeah, it's increasing, decreasing, decreasing, and increasing. So what kind of a point is 3 going to be? Yeah, 3 is going to be a relative maximum. And then this is going to be a relative minimum. It's not an absolute minimum because I'm not guaranteed that this doesn't go below here or that it doesn't go above what happens at negative 3. Overall, let's see if we can't summarize though. Overall, let's figure out where it's increasing and decreasing. Ashley, what intervals is it increasing on? It's actually a little bit more than that. It's just everything to the left of negative 3.
So negative infinity, negative 3.
Yeah, so negative infinity to negative 3. And then let's just come down here. It's decreasing, right? So it's decreasing on what interval? Between these 2 points. So negative 3 to 0. And here's our good old union symbol again. Union what? Decreases from 0 to 3. Is that right? Yeah, 0 to 3. And then increases again from 3 to infinity. Yeah, 3 to infinity. Now, if you actually look at this, we've pretty much got everything except, this little scattering of points. Let's see how this compares to the graph. Before I turn to the graph, are we okay with what we've got right here? I mean, for all our work that we did, that's the solution. So that's it. Now, there's nothing wrong with confirming your work by looking at a graph. Your graph should be telling you the exact same information that we see here. So let's do that. Let's go over to Desmos. And let's see, here's our graph. So perfect. So let's see what's happening. To the left of negative 3, the function's increasing. It keeps on increasing, increasing, increasing until we get to this point. And then it's decreasing. Now 0 is undefined. We've got this vertical asymptote. But between 0 and 3, right here, what's happening to the function? It's decreasing again, right? So it's decreasing here. It's decreasing here. That matches what we had over here, decreasing and decreasing. So if you're wondering, well, how could that happen? Now you see it. And last but not least, to the right here, the right of 3, it started increasing again. Oh, okay, there you go. Perfect. We don't want to graph the derivative. I mean, you can. If we graph the derivative, yeah, let's put up the graph of the derivative and just kind of compare that. So the derivative is going to be y equals 1 minus 9 divided by, what was it, x squared, right? X squared. All right, so let's see how the derivative compares to the function. So to the left of negative 3, notice something about the derivative. The derivative is above the x-axis. So it means the derivative is positive. If the derivative is positive, that tells you that the function's increasing. Now, the derivative is positive until we get to negative 3. What's the value of the derivative at negative 3? 0. Why does that make sense? What's happening at 0 that's special? That's where the function changes direction, right? It goes from increasing, a positive derivative, to 0, and then decreasing. To the right of this, the derivative is negative. So the function is decreasing here. But remember I said we need to test on both sides of 0, even though it's not defined there, the function could change signs there. It didn't. It was decreasing both places. To the left of positive 3, what's the sign of the derivative? Negative. And that corresponds to the function over here is decreasing. It's decreasing until we get to 3. At 3, you've got a 0 derivative, then it's positive. Slope of the tangent line here is positive. So there's a nice correspondence. I'd suggest that you be careful about what you're graphing, because looking at both of them can be kind of tricky. One thing that you can do to help keep things straight when you're graphing is change the style of your graphs. So change the style. Now with the 84 colors, I can just graph things in different colors, and that's great. But if you have a regular 84 that doesn't do colors, here's what you can do. So there's our derivative. Let me put in the function x plus 9 divided by x. So that I can distinguish one from the other, what I'll do is I'll go over here to the left of the Y key, and you press enter, and it changes the style of line. So now I've got a regular line and a very bold line. And then it's easy to tell which one is which when you're looking at the graphs. So I think a good viewing window might be like negative 6 to 6 and maybe negative 2 to 2. You can see one graph. There's the derivative. And then coming up, well, yeah, you know what? We don't have enough. We're not zoomed out enough for the function. So, oh, we can't. There we go. Yeah, thank you. Let's see. I'd need to change the window in order to see that. I think you need to go down to maybe negative 8 to 8. Might do it. All right, so there's the function, and there's the derivative. Or other way around. First one was the function. Second one's the derivative. Whatever. One of them's one. First one's the derivative. Second one's the function. There we go. Do as I do, not as I say. All right. Thanks, Victor. Yes, question?
Something that I kind of forgot, how 0 is undefined, so it's not continuous, but we can still have a derivative?
Well, the derivative is not defined at 0 either, is it? But because the derivative is undefined here, 0 is a place where the function can change signs. So the derivative function can change signs at these points because that's where it equals 0, and at this point because that's where it's undefined. So you have to test on both sides of each of those kinds of points.
Well, the graph is not continuous, right?
The graph's not continuous. That's okay. So we're not probably going to be using Rolle's theorem with this too much, but it still works. Let's move on to problem number 16, unless there's some more thoughts on problem number 12 here. Problem number 16 I chose just to give you a little bit of practice with your trig. Also to remind you of this notation. F of x is sine squared of x plus sine of x. Let's first consider the domain of this function. Are there values for which sine is undefined? No. Sine is kind of like the polynomial of your trig functions. I mean, it's nice and smooth, no places where it's undefined. You can differentiate it as much as you want. So sine is a nice function. Its domain is everything. So domain is negative infinity to infinity. Okay, to figure out where it's increasing and decreasing, we need to look at the derivative. In looking at the derivative, the first thing that I would suggest is you rewrite sine squared of x. And I'm not thinking of the Pythagorean theorem as 1 minus cosine squared of x. Thinking of the chain rule. Let's write it like this. Put the squared on the outside and sine of x on the inside. I think it's easier to see that you need to apply the chain rule here as opposed to up here. If you can do it up here, that's great. Let's apply the chain rule to this. What's the outside function? 2, the squared. So 2 times sine of x to the first power. I'm not going to write that first power. Times what? Times cosine of x. Good, that's the derivative of the inside. So this is the derivative of the outside times the derivative of the inside plus cosine of x again. Great. I need to set this equal to 0 and figure out where the function can change signs. Now, stay with me on this one because it's going to get a little bit involved as far as testing points. The points are going to be pretty ugly. But let's find those points first. Yes, sir.
Is 2 sine of x cosine of x an identity?
It is an identity. It's a double angle identity. So this is sine of 2x. Nice job spotting that. I don't think that's the way to go in terms of solving this. But as far as solving is concerned, when you set this equal to 0, there's something that catches my eye. Does it catch anyone else's eye? Excellent. You can factor out a cosine. So that leaves behind 2 sine of x plus 1. And now I've got something times something else equals 0. One of those somethings has to be 0. So it's a matter of solving. So where does cosine of x equal 0? And this one we can do in radians. At least I hope we can do it in radians. Where's the cosine equal 0? Pi over 2. Good. Where else? Good. Pi over 2 and 3 pi over 2. Now, I'm not going to bother you about, gee, where is this equal to 0? All of them. But in general, so let me just kind of remind you, in general, it's going to be x equals pi over 2 plus n pi. Basically, it's going to be odd multiples of pi over 2. 3 pi over 2, 5 pi over 2, 7 pi over 2, or negative pi over 2, negative 3 pi over 2, etc. The harder one is this one. It's where does 2 sine of x plus 1 equal 0? Wow, I'm impressed. That was remarkably fast. Yes, that's one of them. So you get sine of x equal negative 1/2. Now, just by a show of hands, can you look at that and do you know the radian values of where this is equal to 0? All right, so about 3 of us. All right. So if you're looking at that going, oh man, it's been forever since I had trig, then here's what you can do. Let's keep in mind that sine is which coordinate on the unit circle? Sine is the y coordinate on the unit circle. So let's give ourselves a little bit of a unit circle here, at least enough of a unit circle. There we go. And what I know is that the y coordinate of my point on the unit circle is negative 1/2. So here we go, negative 1/2. And I see that there's 2 points where this happens. My goal is eventually to figure out the radian measure of this. Yes. So it's a negative 1/2 and another negative 1/2. So the question is, What's this angle? Nope. There you go. And this one. So for those of you who don't remember this angle, here's what you can do. You can take x is the inverse sine of negative 1/2. Now when you do that on your calculator, I would suggest you temporarily put it in degrees, because most of us aren't going to recognize the decimal value for that. So mode over to degree. Second, sine inverse, negative 0.5, and I get negative 30 degrees. So, okay, maybe I'm spending a little bit too much time on this, not sure. But that's negative 30 degrees this way, and then this is also going to be 30 degrees. What I want in general, though, is this angle and this angle. Let's figure out those angles in degrees first and then radians second. In degrees, this is 180 plus 30, that's 210. How about this one? What's the second one in degrees? 360 minus 30 is 330. Now some of you already raced ahead and figured this out. This angle is 7 pi over 6. And this one is 11 pi over 6. So now, if we're sticking to just those that first interval from 0 to 2 pi, then these are all our solutions. If you need more, you can add plus 2n pi, multiples of 2 pi to both of those, and get as many answers as you want. Okay. If you're like me, you don't really have these numbers memorized. You don't know what their decimal values look like. So let's calculate some decimal values. This is going to be about 1.57. This one is 3 times as much, so that's going to be about 4.71. 7 pi over 6. Well, that one's that's going to be a little bit more than pi. Turns out to be 3.67. And the last one, 11 pi over 6, is going to be about 5.76. The reason I wanted those values is so that I can put them in order in terms of testing things. Let's give ourselves a little table now. Actually, kind of a big table. So here's our points, x, and then f and f prime. In increasing order, it would be pi over 2, and then 7 pi over 6, then 3 pi over 2, and 11 pi over 6. So those are our points here. Now I'm going to rewrite the decimal values here because we need to come up with some testing points. So as a reminder, the decimal values look like this: 1.57, 3.67. No, that's not right. 3.67. That's right. 4.71 and 5.76. the derivative at all these points was 0. So you would expect to see a horizontal tangent line at all 4 of those points. I need some test values. What would be some good test points here? 0 or 1? Sure. How about the next interval? 2? Sure. 4? 5? 6? Sure. There's no reason to, you don't have to get real crazy on these things, all right? Just choose some simple points. What am I going to program into my calculator? Derivative. You got to be careful about these. It gets easy to get mixed up between the derivative and the function. Let's just put in the derivative. As far as the derivative is concerned, I don't know of any other way to put it in other than with parentheses. Parentheses, sine of x squared. Maybe in some future version of the operating system for this calculator, they'll figure out a way to write it like I did initially. But you need 2 sets of parentheses. Oh, you know what? The function. The derivative. You're right. So that should be 2 sine of x. Thank you so much. 2 sine of x cosine of x plus cosine of x. I just finished lecturing about that too, didn't I? All right. Do as I do, not as I say. Let's go to our table. And there's going to be a mistake, and maybe you'll catch it, and maybe you'll catch why. I'm going to delete all my values here, and then type in 1, 2, 4, 5, and 6. Is my function always increasing? No. Well, wait a minute, though. The derivative is positive for all these. I don't get it. What's going wrong? It looks suspicious that a function would always be increasing here like this, because I know sine goes up and down a lot. Same with sine squared. So can anyone figure out what's going wrong? I'm still in degrees. Remember, calculus is done in radians. So most of you probably haven't changed over your calculator to degrees to follow me on that previous calculation. But when I switch back to radians, then I get what I'm supposed to.
Mine was already set the right way, so I thought I did it wrong. Like,
Oh.
your values are different.
Yeah. No. You did it right. If you got something like this, then you did it right. Cool. You go to the mode button, and then one of these options will be radians. Just put the cursor over that and press enter. Cerise, what do I need from this table? Yeah, from there. Good. I need to know where it's positive and negative. Perfect. So it starts out positive, and I think it alternates from there, right? So positive, negative, positive. Yep. All right. So positive, negative, positive, negative, positive. Perfect. Matt, what's that telling me about my function?
That is increasing.
Increasing, decreasing.
Increasing.
Mm-hmm.
Decreasing.
Perfect. So, Dom, what kind of point must I have at pi over 2? What's that going to look like on the graph? Yeah, a relative maximum. And I appreciate that you said relative, too. Good job. And the next point, the function's decreasing, then it starts increasing. This has to be a relative minimum. Relative max. Relative min. Nice. Let's put it all together in terms of where it's increasing, where it's decreasing. So it's increasing. Now I'm just gonna I'm just gonna limit it to 0 to 2 pi because we're not really analyzing it to the left of there. So I go 0 to pi over 2. Where else is it increasing? From 7 pi over 6 to 3 pi over 2. and from 11 pi over 6 to 2 pi. Now chances are it's increasing beyond that, but we're just limiting our work to the interval 0 to 2 pi. 2 pi. 2 pi. Yeah, I just don't want to get into, you know, trying to characterize this in an infinite way. As far as decreasing is concerned, that would be from pi over 2 to 7 pi over 6, and from 3 pi over 2 to 11 pi over 6. Yay. Wow. Good on us. There's your final answer. Are we okay with our conclusion here? The one thing that I want you to have practice with and get a little comfortable with is what we did here. Coming up with some decimal values and then having to test points in between there. Yes, ma'am.
Does it matter when we found the decimal values, whether your calculator was in radius or degree?
No. It's a good question. Yeah. It does not matter. Also, you don't even need 2 digits to the right of decimal. 1 digit is fine. You just need a good approximation. So if you know that in your head, great. Let's compare our conclusion here, to the graph. So shut this one off. Here's the graph. Let's kind of zoom in a little bit. The advantage of doing it on decimals is that it can display some of these nice points. So the function we concluded was increasing from 0 to pi over 2, and there's your maximum point, right? And then it dips down, it's decreasing until 7 pi over 6, and if you zoom in a little bit more, you can see that there's this tiny little interval where it increases for just a little bit, decreases for just a little bit, and then starts increasing again. So, nice. Okay, now we stopped our work at like 2 pi, so that's all right, but you can see the next maximum. Are you comfortable with problem 16? Charlie, that's a yes? Nice vigorous nod. Thank you, sir. Okay. Let's try. We're going to do some more here. Let me just take a look. Might change things up a little bit. Let's try problem number 40. So back over here. For problem number 40, f of x is a rational function, x squared minus 2x plus 4 over x plus 1. See if we can't get that in focus. So, okay. Where should we start? What do you think we should do first? It's a good question. It doesn't factor. Before we differentiate. Yeah, domain. Good job. So the domain, what can you tell me about the domain? Good. X can't equal -1. Thanks, gentlemen. We will have to kind of keep an eye out for that point. The function and its derivative will be able to change signs at that point. That's okay. As far as f prime is concerned, we need to calculate the derivative. Maybe I should give you a chance to work on that. So go ahead, work on the derivative. Use the quotient rule for this. Now, after you get the derivative, I strongly suggest that you simplify it. See what you can come up with. It actually does simplify pretty nicely. Okay. Let's take a look. Did I copy down the problem right? No, I didn't.
That's why I couldn't
I
remember.
I'm sorry. I'm really sorry. I'm really, really, really sorry. Yeah, because when you get down to it, if yeah, that should be a 1, shouldn't it? Oh man, man, I I feel bad. I really do.
Can we write problem 40 at the top of our next
Problem 40-ish. No, this is actually problem 40. What we did was problem 40-ish. I feel bad. You guys are at least being good sports about it. I hear various levels of protests every now and then when this kind of stuff happens. There's the really loud erasure, and then if somebody really wants to send me a message, I hear like that, and I feel really bad. I do. I'm human. Yeah. Oh, 2 of them. Oh man, hurt me squared. All right. Yeah, my bad. Yeah, that should be a 1 here. All right, fine, fine. Write problem 40 next to your name on the next test, okay? Get a little point of extra credit. 40-ish. 40-ish. Well, let's do this one together then. It does work out if we had the right number. When we differentiate a quotient, you start with the square of the denominator, and then the denominator times the derivative of the numerator. Derivative of the numerator is going to be 2x minus 2. And then, that's not those worst things that could happen to you. And then, let's see, the numerator, which is this, 2x plus 1, times the derivative of the denominator. Derivative of the denominator is just 1. Okay. If you distribute and FOIL here, by foiling, we see we get these 4 terms. I'll distribute a minus 1 here. You get something like that. Now there's a lot of nice simplification here. The 2x's cancel each other out. And I've got like terms here and here. 2x squared minus x squared leaves me with x squared. So this factors into, or simplifies to x squared plus 2x minus 3. So a long time ago I warned you that we're going to need to do things with our derivatives, so you're going to need to get in the habit of cleaning them up. This is such a case. This continues to factor. It factors as x plus 3 times x minus 1. So that's our derivative. That's f prime of x. I need to know where that can change signs. This can change signs where the numerator equals 0 or where the denominator equals 0. So Liam, what are those points? Where can this change signs? Good. So -3, -1, and +1. If I list those in order, it's going to look like this. Now, you need to plug in the you need to plug in the function or the derivative into your calculator and do some testing of points. Are you comfortable with that? Can I kind of bypass that? All right, so make sure that you're careful about choosing test points. For instance, here I want to choose -4, not -2. And over here, maybe I'll choose 0 and then 2. Turns out that this is positive, negative, negative, positive. So the function is increasing, decreasing, decreasing again, and then increasing. How about our point at -3? Is it a relative min or a relative max? Relative max. That's what's called the first derivative test. You look at the signs of the derivative, how it's changing at a critical point. If it goes from positive to negative, it has to be a maximum. If it goes from negative to positive, then it has to be a minimum. As far as the function itself is concerned, it's increasing, not negative 4, negative infinity. It's a negative 3. Negative infinity, negative 3. You're making me feel better. Appreciate that. And then where else is it increasing? Yeah, 1 to 2. Good job. No. Thank you. All right. 1 to infinity. And then as far as decreasing is concerned, please don't write negative 3 to 1. I'd be a little uncomfortable with that. The function is not defined here at negative 1. So just spread it out over 2 intervals, negative 3 to negative 1, and from negative 1 to 1. So something like that. Always answer with intervals along the x-axis. Yes?
So there's a relative minimum at negative 3 and a relative minimum at 1.
There's a relative maximum at negative 3 and a relative minimum at negative 1.
But nothing is negative or
Relative minimum at 1. So nothing is negative 1. What's happening at negative 1? Yeah, you got a vertical asymptote. So let's shut this off. Let's graph the actual function. So it was x squared minus 2x plus 1
X squared looks kind of weird. Oh, never mind.
divided by x plus 1. And let's turn that on and kind of zoom out. So this matches our expectations. You can see that at negative 3, you got a maximum, right? At positive 1, you've got a minimum. And at x equal negative 1, you've got a vertical asymptote. Not that's necessarily shown here, but we can add that in. X equal negative 1. Let's turn on the graph. There you go. There's your vertical asymptote. You're not going to see that on a good graph, but it's there.
but that does not exist.
I wouldn't put that as part of the graph at all. I'm just showing you that that is a feature of the graph. Are you comfortable with problem number 40 there? Now that we read it the right way. So, okay. Again, sorry about that.
Do we put the does not exist and then negative 1
On the chart, if you wanted to fill in the chart really carefully here, then you'd have zeros here and here, and in between here you'd have the does not exist. Or you could also write undefined. That's fine. I'm not really looking for a symbol or something here. Part of the reason I'm putting this stuff here is because soon enough we're going to start graphing these types of functions. So I'm going to be putting points here, and it's nice to know what happens to the derivative, the value of a function at a point, etc. So we will want to complete that more later. But right now it's pretty good. Okay, it's all right. I'll take a little bit of grief today. I screwed up, so. Let's do one last one. Problem number 48. (48) or 48-ish. It's going to take me a while to live this one down, isn't it? So 2 years from now, I'll see it on Rate My Professors. Yeah, you screwed up problem 40, man. F. Yeah, don't take his class. Or skip the day he does problem 40 in section 4.3. All right, problem 48. f of x is x arctan of x. Okay, so let's work on the derivative for this function. In differentiating it, what's the rule that we have to apply here? Somebody mentioned back here. Product rule. So you've got u times v. Derivative is going to be u prime v plus v prime u. So, we don't necessarily need to use a chain rule because there's an x here and an x here. So there's no.
No, I mean you use the chain rule to get the derivative of v.
No, it's going to be. Yeah. If this was an x squared or like on your test an e to the x, then you'd have to use a chain rule. But because there's just an x in here, the derivative of the inside is just going to be 1. So I wouldn't necessarily think of using the chain rule. I mean, technically you could apply it. So I want u prime v minus v prime u, or plus v prime u. U prime is going to be 1 arctan of x plus x. What's the derivative of the arctan? Well done. Almost in unison. Yeah, I was thinking the same thing. So, arctan here, and now I want to know where this is 0 or undefined. It's not going to be undefined because x squared plus 1 can never equal 0. It's always going to be a positive number. The challenging part for you is going to be figuring out, well, where does it equal 0? Where could it change signs? So let's use a little technology. Let's graph them. Yeah, I'm all about the technology, right? So put in the derivative, but where's the arctan button? I don't see an arctan button on my calculator. Second tangent, right? So make sure you're plugging in the derivative, not the function. Second tangent of x, close parenthesis, and then this part over here, I'll just write it as x, so plus x divided by parentheses 1 plus x squared, right parenthesis. So there's your derivative. Yay. That's all right. As far as graphing it's concerned, let me suggest a window, say from, I don't know, -6 to 6. It's almost -2 pi to 2 pi. So -6 to 6. And here, let's go from, say, -3 to 3. That should be more than enough. Press the graph key. But what are we trying to figure out here? We're trying to figure out where the graph is equal to 0. What value of x does that for us? 0, right? At 0, the function is 0. At least the derivative function is 0. So, in fact, that's the only place where the function actually changes signs, right? At least the derivative. It goes to the left of the y-axis. That is x less than 0, the function has a negative value. To the right of it, it's positive. So let's see if we can't fill in a chart. In fact, we don't even have to test any points. This will be nice. So x, f, f prime, and 0. Well, at 0, the function has a 0 derivative. Okay. To the left of 0, what's the sign of f prime? Negative. And then positive. So the function is decreasing, then increasing. Okay. All right. To shut off a graph, if you want to just if you want to keep the first derivative around but not graph it, put the cursor on the equals key and press enter. That'll shut it off. And now I can look at the graph of x arctangent of x, which would be the inverse tan. I'm trying to think if I want to adjust my window. I am going to adjust my window. Let me go from, say, -4 to 4, and let's do 0 to, we'll do 5. That's just a guess. Ooh, that was a pretty good guess. That was a really good guess. I like that. I did. Thank you. So, does this confirm what we saw? Absolutely. The function is decreasing until it gets to 0. You have a minimum point at 0, and then it starts increasing. So the derivative is negative here, and then positive here. And 0 briefly at that instant, right at the origin, when x equals 0. So, cool. I strongly suggest that you make sure that the information you're getting from here matches your graphs. I mean, short of me giving you an answer key, that's the one really good way that you can check your work before you hand in an exam. Yuri? Well, this would be, if you're just looking at this, it has to be a minimum. In fact, it's not only a minimum, it's an absolute minimum. The function doesn't go below here. It can't. Because it's decreasing forever until it gets here, and then starts increasing. If it was to get below this, then at some point it would have to decrease again, at which point you'd have a 0 tangent line. So since there's no point which the function turns around, this has to be an absolute min. It just can't get below that. And so that's why I can get away with graphing this with a value of y minimum at 0. It's just not going to get any lower than that. So great question. Thank you. Okay. I think that's good enough for this section. I had wanted to do problem number 28. You know what? Yeah, let's just do problem number 28 because it has a little factoring trick that you missed on your last exam that I want you to get. So let's try this again. And basically this is my little warning heads up that you should be ready for it on future exams. So f of x is x plus 2 squared times x minus 1. So this is a cubic polynomial. Yeah, okay, that's nice. It should be pretty friendly to work with. Its domain is everything. Negative infinity to infinity. So we're okay there. We don't have to worry about any strange points where a denominator is 0. As far as f prime is concerned, we have to use the product rule and the chain rule. So Matt, here's your chance to use the chain rule. So I want to calculate u prime times v plus v prime times u. What's u prime going to equal?
2 times x plus 2 to the first.
Good, to the first power times the derivative of the inside, but what's the derivative of the inside? Times 1. Good, so I'll put the 1 there just as a reminder that we had to use the chain rule, even though it really doesn't affect our calculation at all. Good. How about the derivative of the second times the first? All right, so it's going to be plus 1 times x plus 2 squared. Now here's the important part. We're going to need to eventually factor this and set this equal to 0. So rather than distribute this, FOIL it out, FOIL that out, etc., yeah, the trick that you want to use here is to factor out the greatest common factor. There's an x plus 2 term that's part of both of these. So, Scott, let me factor out the x plus 2. What's left behind? Well, we took out one of those times x plus 2, or plus x plus 2. Perfect. Now, let's combine these things. If I distribute the 2, I get 2x, plus x is 3x, minus 2 and plus 2. Oh, wow. What happens there? What's left here when I distribute? Just 3x. Maybe I should do that out. Maybe that's a little bit too much. If you distribute this, you get 2x minus 2 plus x plus 2. The 2 and the 2 cancel, right? Those cancel. X and 2x gives me 3x. So, wow. That worked out pretty nice. I guarantee you it's a lot less effort this way than if you distribute here, FOIL out here, collect like terms. Wow, that's a lot of work. So are you seeing this little trick here? It's something I want you to know. In fact, on the last test, I thought about giving you something a little bit more. I thought about putting like a 5 here and a 4 here, but I stuck with the 2 and the 1 that they had in the book. But, on future tests, I want you to know that trick. Where is this equal to 0? Yeah, x equals negative 2 and 0. So you put those on a number line. X, F, F prime, negative 2 and 0. And I'm just going to kind of rush through here. When you test test the first derivative here, you're going to get positive, negative, positive, increasing, decreasing, increasing. All right, the rest of it I think you can handle as needed. The thing that I wanted you to get the most was the factoring trick. So are you comfortable with that factoring trick at the end of that? All right, thank you. Let me give you some homework. Back to almost. If I had forgotten the homework, then I would redeem myself. Section 4.3, homework. Try 1 through 17, 21 through 39, 45, and 57 through 63.